processing of paints, plastic, and elastomer-based composites. So today I have arranged my deliberation into 4 major heads, like I usually do. So first thing, before I really interact with you of the screen, so I'll give a first weekly summary. Weekly means so far, so forth. 4 weeks have been covered. Okay, with that anticipation, I'll cover up what exactly I covered during the courses, during the deliberation, basically. Then I'll try to pick from the forum questions. You have a couple of those, but I'll try to address them very quickly. Okay. I'll then go to the little bit elaboration on what I'm going to talk about for the upcoming next 4 weeks. Okay. And then finally, the live questions and answer, I'll deliver it upon. Okay. So that is what. Let's try to quickly see what have been covered so far, so forth. Okay. The week first, if you ask me what I actually exactly covered, is basic introduction to polymers, structure-process correlation, basic rheology, classification of fluids, and flow through various channels. So at least the first parts, excepting the fluid part, is quite similar what I covered in my another NPTEL rerun course, which is running over, last semester also it was there on characterization. Okay. So again, in basic introduction, I try to classify polymers in terms of their structural and property attributes, basically. And then finally, we try to have a structure property correlation, which is the basic foundations of polymers, polymer science or polymer technology ultimately in the long run. Okay. So I talked about types of bonds. So for example, you have a covalent bond in the main chain backbone, and side by side, you have interaction of the chains forming a secondary bonds. And based on that, you know that, interaction, and some of the interaction which you call it a cohesive energy density, eventually we define based on the bond strength and sum of bonds across the, whole length of the polymer, okay? And it, whether it exists in a, at room temperature or normal temperature and pressure condition, whether it exists as a rubber, plastic, or it is a fiber. Okay. Then I talked about heat of dissolution, which is a little bit on the picking up from the thermodynamics of polymer solutions. Bit on solubility parameter. Again, I'll say it's a bit, it's just the basics. It's not the, if you really have to refer to the polymer thermodynamics, solution thermodynamics, you have to refer or start from the PJ Flores books, okay? Statistical mechanics of chain molecules that I talked about there, okay? Then about the bond rotation forming innumerable conformers and basic structure property correlationship based on various structures, okay? So that is very common one. But what is unique in this particular course, we started defining rheology, which is essentially a flow and deformation of the material, and that ultimately, linked to the not only the property but finally to the processing aspect. So it becomes more like structure, property, and process correlation. Essentially, it is. So I talked about what deformation means, basically, what type of different modes of deformation that can be possible. Okay. I talked about eventually the shear stress, shear strain, and shear rate. Shear rate is gamma dot, if you recall. Okay, gamma dot is the rate of, is related to rate of deformation, basically. Okay. Then, whenever you have a relationship that exists between the shear stress and shear strain or shear rate, you call it a constitutive. So I again will revise if you are mistake there. So what is a constitutive equation? What is a kinetic equation? What is kinematic equation? Okay. So here we more of focused on constitutive equation rather. But if you look at a stress, for instance, it's not a vector, it's a tensor. Okay. You imagine a 3x3 matrix. Okay. And its diagonal element, if we remember, if I applying in tension or compression, the diagonal elements actually defines the shear mode of deformation. Okay, and difference between them, say for example, sigma 1,1 and sigma 2,2, sigma 1 and sigma 3,3, those are called normal stress differences. Okay, and this normal stress difference has a lot of implication finally to the processing or a kind of shape you get out of after the processing, say for example. Okay, so we try to briefly define again, I mean, Hookean, non-Hookean slide the glimpse of viscoelasticity, what pretty much any polymer is, whether it is in a solution state, whether it is in a normal state or in the molten state, say for example. Okay, so accordingly, there are two types of tests you can make it for a viscoelastic material. One, say for example, can be quasi-static type. Say for example, creep and stress relaxation experiment. Another one is a dynamic one, which is a directly dynamic mechanical properties that I emphasize separately. Okay, I talked about Newtonian flows, Newtonian fluids, and non-Newtonian fluids, of course, and several rheological models that depicts a fluid, say for example, which is a Newtonian you know already, okay, but about the non-Newtonian one, okay. So Newtonian means which follows the Newton's law of viscosity, okay. So you know it's a eta equals to your sigma by gamma dot, say for example. Now, very quickly to brush up again, if you look at a fluid, let me take the pointer for your convenience here, okay. Very quickly take the pointer option here. So if you look at fluids, it's you can pretty much have an ideal fluid, real fluid, and at the end a Bingham plastic, which is a special type of a fluid here. Okay, so in the real fluid, actually, that normal fluids exhibits, real fluid exhibits the Newtonian and non-Newtonian classes. Even in the non-Newtonian classes, you can again classify them into time-dependent and time-independent fluid, okay? Time-dependent and time-independent fluid. In the time-independent fluid, you have pseudoplasticity, dilatant. In fact, Newtonian also you can pretty much group it here also, okay? And you have the time-dependent fluid, which is the thixotropic and zeopectic fluid. And based on that, what type, how does the viscosity changes, essentially. So this pretty much defines the classification of fluid from the basics point of view. It's again a very basic segment. We try to hit it on. Okay. And then we try to go a little bit into deeper insight into the flow. Okay, flow through, most precisely on the channels, which is pretty much the real scenario. Either your fluid or your polymer will flow through a channel to finally give it a shape, or flow through a conduit, flow through a channel, say for example. Okay. So, again, you can depict the flow by Arrhenius equation, say, for example, okay? So you all know Arrhenius equation is goes through activation energy barrier, essentially, okay? State 1 to state 2, and that, free energy difference between this initial state and the, intermediate state or transition state, you call it activation energy. Okay? And then you have a non-Newtonian fluids, and then its activation energy. I talked about the WLF equation, William Landau-Ferry equation, which is pretty much based on the free volume theory, basically, and Dunedin's law that I elaborated. And then open channel flow, the steady and unsteady flow, and most importantly, laminar and turbulence flow, okay, and which is which you can discriminate by a number which is known as Reynolds number. Above Reynolds number, critical Reynolds number, the flow is supposed to be turbulence, and below that is laminar. But for polymer, imagine one thing: it has a very high viscosity. So in order to achieve a turbulence, it's very, very difficult to have a turbulence. The velocity is going to touch upon almost to the escape velocity tune. So you cannot really achieve realistically the turbulence for a high polymer, whether it's a molten or in the solution state, basically. Okay. So I talked about a concept, okay, a boundary layer, okay. It's a boundary layer concept in the steady state fluid. We really have to visualize the velocity lines of it, okay. Then boundary layer developments over a flat plate and development of boundary layer in a closed conduits in pipes, for instance, okay. Then continuity equation, then most important in fluids in any form, not only in rheology, but also any fluid you consider, whether it's aerodynamic flow, whether it's a flow of a fluid whatsoever, okay, for heat transfer, okay. So it's a Navier-Stokes equation that I elaborated. I essentially give you the concept of pressure drop. What you mean by pressure drop? Once a fluid is flowing through a pipe from point A, which is the entrance to the exit, what is the pressure drop of it? That also is very important to realize or conceptualize or quantify the flow of material, and then relative roughness of a pipe. That is also important. I forgot one thing. While talking about the normal force differences, the first normal force differences actually signifies some of the properties that you get it in a viscoelastic material, like a diaxial, say, for example, for our another terminology which is quite common, it's called calendar shrinkage, for example. But if you look at the surface roughness point of view that I was talking about just now, if you look at it, it depends on the second normal force differences. So not only computing viscosity as a function of shear rate, but as well, this normal force differences as a function of shear rate is very, very important while predicting the shape of the material, while predicting the roughness of the surface that you make it by a unit process. So these are some of the implications in the long term that will again, invoke it, call upon again as and when required. Okay. So summary of week 2, we again give an introduction to various viscometers, which is a measuring arm of a rheometer. Okay, and rheometric techniques, implication of master curve. No single viscometer or no single rheometer can give you a viscosity data helps you to realize over a wide range of shear. So, for example, if you look at a realistic processing, you have a compression molding. In the compression molding, it works at a shear rate typically of the tune of tens of second inverse. If you look at that, so for example, transfer molding, it's 100 of second inverse. If you look at extrusion, it's of the order of thousands of second inverse. Okay, that is what the quantum of shear rate involves. Okay, in injection molding, 10,000 second inverse of that tune. So you have to really realize a wide range of shear rate. Not only that, even below 10 second inverse, you have certain processes, say for example, casting that involves low shear rate. So in order to realize, in order to predict what is going to be the behavior of the material had it been processed by a unit process, that actually helps you to do it. So you have to generate separate geometric measurement, lay them in a curve, which you call it a master curve. Okay, and there is a conception of time temperature superposition. There are other conceptions available, mathematical equation available by which you can overlay your measurements by different rheometer and apply appropriate shape factor and try to lay them on the master curve. That's what the conception. This conception is quite common. Whether you do it for a DMA, which you call it TTS, for example, is a conception dimension. One thing I must tell you one thing. Some of you are asked the question. Okay, see DMA and geometric measurement, somebody asked, what is the difference? Geometer can be done in a static manner, okay, or quasi-static manner, where your time is extremely, constant. Okay, another one you can do in a dynamic way. So if you apply a dynamic stress and try to measure the dynamic strain, or measure a dynamic stress and try to see what is the dynamic strain rate. So from that you realize two numbers. See, it's a viscoelastic. One point you realize it as a Hookean solid, another point is a Newtonian fluid. Okay, whether you realize it in terms of viscosity when you consider it as a more of fluid character, you try to realize as a modulus when you consider it more of like a solidus character. Okay, so if you try to do your measurements at a extremely at the higher temperature side, the material behaves more like viscous material more than that it is a solid as character. So you call it like a rheometric measurement in dynamic rheometric measurement. Okay, dynamic rheological measurements, and the same thing. Once you do it at a lower temperature, you call it dynamic mechanical properties. So it really doesn't make much of a difference in terms of conception. Okay, so DMA or rheology once again is an inherent property of the material. Is nothing very unique. Nothing. It's very widely separated from dynamic mechanical measurements. But conception-wise, you have to just try to see the quantum of temperature involved and equivalent frequency, which is otherwise in rheology you call it shear rate, that is involved. So that is what you have to do interpolation, extrapolation in terms of mathematics, if I have to say physical. So now again coming to the point where we were, the flow of the liquids in various channels, as I told, like melt flow analysis at every frame by frame you have to analyze it. Okay, and then you have to just try to solve try to compute the average velocity. So for example, instantaneous velocity. So for example, okay, so laminar flow through a circular cross section, velocity distribution. Now You try to apply in the same flow pattern, try to realize putting different constitutive equations. Say, for example, power law equation. Okay, so try to see. Put it in another complex fluid form of it. Okay, say for example, Caro or Shuda sort of a fluid. Try to analyze the flow, get the final solution of it, and try to see how the average velocity looks like basically. Okay, so similarly, flow between parallel plates, flow through anneals, transition between again in those flow pattern, laminar to turbulent. When you are realizing the turbulent, whether my Reynolds number is absolute or I have to realize with a different number system based on that type of flow involved basically. Okay, and this is what is more important to realize you. But one thing I'll say, whatever is taught here, you try to solve yourself. Okay, unless you solve independently, just try to mug it up from a textbook or my lecture, whatever I provided, the derivations, you try to derive yourself and try to better have a hands-on realization. That's why in one of the module, probably in the last module, I kept some numerical problems so that again to brush up your ability to solve numerical problems that you did probably during your 9th standard, 10 plus 2 standard, and for the entrance examinations, for example. Otherwise, you won't be able to match up. I mean, the exact real expertise I want to have it out of this course, and you'll be benefited from that. Okay. So now we try to talk upon the rheometers in a more concise manner, focused manner. We talked about a capillary or glass viscometers. We talked about rotational viscometer, falling ball or falling piston viscometer. As I said again, viscometer is not a single or universal viscometer exists. It can be a different types of viscometer. And finally, it's the whole idea is to compute across the whole range of shear rate. Okay. Otherwise, I mean, the maximum you can assess experimentally is better, although there is some interpolation, methodologies and mathematics that again will be a little bit approximate. Okay. Based on the approximation or boundary condition you put in. So we try to cover for polymer the most important rheometers here. So capillary rheometer, which actually measures very high shear rates. Okay, and a rotational dynamic rotational rheometers. So for example, like parallel plate and Conan plate rheometer. Okay, and both in the oscillatory form and quasi-static form. And torque rheometers are very, very important for rubbers, which is of high viscosity basically. Okay, high viscosity of the tune of 100 kilopascal second of viscosity, say for example. So in general, we try to touch upon the general viscometer possible measuring. I mean, material includes rubber, plastic, and fibers, as well as this high viscosity, as well as paint and adhesive, which is low viscosity. It's Oswald viscometer, Brookfield, say for example, the adhesives and paints, you can very pretty well assess. Oswald viscometer is a very preliminary viscometer, the concept of flow, okay, of a certain length in a capillary tube. So for example, falling piston viscometer. So each one of the viscometer or rheometer has its own limitation and of course advantages. Okay, so based on that, what you are targeting the measurements, what sort of information you want to fetch in by geometric measurements, okay, that you have to choose. Okay, so for plastics, say for example, I mean, MFI is good enough. MFI is you have a specified load given at a certain temperature. With that given load, how much at a given time is actually flowing across a particular length of capillary. Okay? Nowadays, MFI machines are becoming more like a capillary rheometer rather than isolated or single discrete loadings and its flow patterns. You can do it at a variegated loading conditions, variegated temperature conditions, and whatnot. Okay? Plastometer, once again, viscometer, plastometer. Plasticity, viscosity is no different. Actually, it depicts the opposite sense of it. Viscosity is a resistance to flow. Plasticity is the ease of. You understand? It's just in the opposite sense, basically. Okay. Then I talked about Mooney viscosity, which is again more like a torque rheometer. It gives you a measurement of a torque that's required to rotate a rotor across the material, which the rotor is embedded into the material, and you measure basically resistance, and which is ultimately culminates to the measurements of the molecular weight of the material. Okay. So that's what we do for a routine analysis, particularly in our industries. Again, this OD or MDR are technically not the rheometer. Rather, we'll call it a cure meter. It helps you assessing cure characteristics. Although from cure curves, you get a lot of information about the flow of it. So, for example, if you look at it, say torque versus time, that's the information you get it here. Okay. So if you hit it out, it goes to a minimum torque and then it cures and goes through either it goes to remain flat or it goes to marching or it gives you a reversion when the degradation happens, basically. Okay. So this minimum viscosity here, okay, this viscosity signifies the ease of flow. So this rheometer gives you although the basic information about the time of cure, but also at the same time from the minimum torque, you will have a measure and how much the ease of flow will be of the material. So remember, the same machine I can use if my conception is quite clear. So then we go to the flow properties of the main characteristics, and then shear modulus, which is stiffness of the material, the maximum minimum torque, optimum cure time from the rheometer. I'm not going into the details of it. I think I have given you enough elaboration of it. Then elastic viscous torque, overcuring. Elastic viscous torque comes from the MDR, moving diometer. Then marching, plateau, reversion, tan delta concept comes from MDR. And then there are rubber process analyzer. This is the rheometer, I'll say. Crude rheometer, not a very precise one as compared to what you see in a parallel rheometer, but at the same time, you can measure, green rubber, which is not cured, which is going to be cured, and after cure. Both three states of a rubbery material assess its flow characteristics as well, the property. So two things important: initially flowability during processing, and then finally, once you cure it, your maximum torque you develop, that actually measures the delta torque, which measures the final property of the material. I have the delta torque, better is building the torque. Okay. Then I talked about shear stress, shear rate, stress relaxation, and gamut of dynamic oscillatory measurements. Okay, angular displacement and angular velocity. So two types of measurements in a dynamic rheometer. How you do it, that is also well elaborated there. So I'm sorry I have written that in this dashboard already, but again, I try to cover parallelly not only the parallel rheometer but also DMA in light of rheology. In light of rheology means, again, you have to assess the terminal part of the master curve. Remember what is master curve means? Like modulus as a function of, see, G prime or E prime as a function of, say, time or temperature. It's equivalent. Let's say time or temperature. Okay. So you get to have a glassy state, glass transition, and then, finally rubbery plateau and flow. And this is what is that flow, and material becomes more like a, liquid state. And in that particular, longer time and higher temperature, the behavior or attributes, you call it like a, geometric significance it has. So that way, viscoelasticity and resilience, how does DMA works, different geometries, in tension, in shear, and also in torsion and compression. So, for example, dynamical testing and their extreme responses and different viscoelastic parameters, DMA data, and modes of DMA. Say you do the measurement in a frequency sweep mode, where you keep rest of the parameters like temperature or time constant. Amplitude sweep, you vary the amplitude, then keep frequency and temperature constant, and sweep. So those are the modes you do it, and that gives you a gamut of information in terms of flow, in terms of filler, how filler exists in a polymer, filler aggregate breakdown, which is essentially called pain effect, and so on and so forth. Okay. So measuring TG from DMA, effect of cross-linking on TG, effect of cross-linking on modulus, effect of temperature on visco elasticity. I think I'm going a little slow today. It's a brush up after all, but again, to cut the long story short, these are the things I did, different methodologies, making a master curve to cover it, the wide range of temperature, two rheological data, how to superimpose by Proximate principles, its limitation, application, and whatnot. Then we went into the application of rheology. So far we understood rheology there, okay? Then how to apply, okay, in paints, plastics, fibers, and rubbers. We talked about working principles of capillary rheometer. We talked about advantages and disadvantages of capillary rheometer, shear stress, shear rate calculations, Rabinowitz corrections, for the non-nutrient fluids, well, flow through a channel, the data you are getting, that's not absolute. So you have to take care of the pressure drop conditions. You have to do the Bagley corrections for the pressure drop corrections, Mooney sleep correction, those to how to pitch in, I know, middle part of the water. That's a good, there are some errors. You take the, corrected data, and then you try to estimate first normal force difference, which measures the dice well or calendar shrinkage. I told already, second normal force differences about the surface irregularities or undulation. So that I have covered very briefly. So most importantly here I got a scope of giving you some idea about the paints. Those who are from paints background, it's very basics for them. Those who are learning polymer science, they get a new science there of paints technology, basically new technology there. And in that, I talked about briefly manufacturing classification, but most importantly, what I covered up in terms of applications is sagging behavior, it's application behavior, storage behavior, what rheological data is important, and it amounts to which shear rate that I have elaborated one by one. If you recall, please, if you forgot it, you already have, I guess, so video. You go and try to run the video, try to see that particular relevant portions. In terms of different shear fluid models, starting from power law, that means the 2-parameter model, to Bart-Caro law, Prof law, Bingham law, which are 3-parameter model, all the way to 4 and 5-parameter models is well depicted. These are the mathematical equation, or you precisely call it a constitutive relation, and that is given. And that you apply fetching in your particular process, and try to have a solution, and try to see how your surface is going to look like, how its diameter is going to be. That's what is the ultimate goal of this particular topic. So then I talked about again in details rheology of paints, viscosity measurements, various rheological studies, shear thinning behavior, thixotropic behavior, long stop storage. Okay. Then we did some case studies on terms of paints, which is UV curable, as a special type of paints, impact of the particle loading because you have a pigment always in the paints, and then polydispersity of the flow behavior and the factor that affects the coating rheology. While coating, what is by brushing, by spraying, what is the amount of shear rate involved. Rheology of adhesives on sealant, I got a scope. I just tried to touch upon very, very, very adhesive science again is a lot of industries runs on that basic fundamental principle. But I try to give you some of the basics, particularly in terms of determining the adhesive strength, handling and stability, various rheological tests on different adhesives, dynamic time sweep test for the curing and shrinkage evaluation, pressure sensitive adhesives, dynamic frequency sweeps, and time temperature superposition, axial test, rheological test for hot melts. Okay, hot melt adhesives are a particular class of adhesives. Then rheology of plastisols, rheological test on silicon sealants and UV curable adhesives. Okay, you remember each of them, each of the segment I depicted later is actually a subject of its own. Okay, but nonetheless, you got enough introduction on that. So again, rheology of fibers and plastics also very briefly again discovered. But remember, rheology of rubber is more complicated than all this material. The reason is why? Can anybody answer? Sorry, I forgot. It's an offline class. I mean, it's more of the molecular weight. So rubber is the longest molecular weight. So the longest molecule is like just a fat man. It is sluggish in terms of flow. That is reluctant to move very fast. Okay, so you have to really make the reluctant people move through a narrow channel or a place. So this is your challenges. Okay, then a little bit about the elongation of flow that is important for fibers. Okay, particularly how to while making a filaments, for example, and then filaments to make a yarn to whatnot rope, and then you weave several yarns. But I'm not going into that details here. It's beyond the scope of this particular class. Okay. Subject. So rheological test on silicon sealants and UV adhesives. So numerical problem again. I got only 4 to 5 short example I've shown in the class. Okay, but there are plenty of numerical problem that arises out of the discussion I have made. The theory I taught you so far, you try to solve yourself. So some of the solutions, if you can do it yourself, it will be easy to solve a complex solution which demands the computation basically. So that is the whole essence of this particular course is. So then I've given a practical demonstration on Oswald viscometer, Mooney viscometer, plastometer, ODR, MDR, RPA, DMA, capillary ionometer, etc., etc. So this just to see if your organization are concerned or in the university, if you don't have the facility, try to visit the nearby facilities, try to do more on hands-on. The demonstration I have given only videographic representation of it, okay? That essentially may boost your interest, but that really doesn't make you expert on that, okay? So remember, it's an online demonstration. You can always side by side on top of what I've given, you can try to see YouTube videos or howstuffworks.com, that kind of a website. But most importantly, you have to practically, handle those gamut of geometer, viscometer, DMA, and capillary ionometers. Then only it will be very, very clear to you. Hope this discussion is good enough. I met it really lengthy, so almost 35 minutes I spent on that. So now quickly going into the forum questions. Okay, Mr. Bhupati N. Your question is numerical relationship between rheology and physical properties of rubber compounds. How to correlate with physical properties through rheology. Now, at this juncture, I'll say what I told you, I'll get you here. Then as I told you, so dynamic mechanical properties, what it measures? It essentially measures the modulus. Okay. Again, if you look at a modulus, say if you look at the composite modulus, which is the dynamic modulus, that means modulus as a function of time, I'll say. Okay. And then which is actually starred in a composite modulus, it's going to be consisting of, E prime, okay, which is represents storage modulus or absolutely elastic modulus, plus another with the imaginary factor, you have another modulus called, remember, E double prime. Okay, so this is the storage part of it. It represents more of the viscous character of the material, and this is a viscous character of the material, viscous. Okay, and this is your elastic character of the material. So what you are getting is nothing other than two component of it. It's giving you one is elastic, another is viscous component of it. Okay, so these two, if you take a ratio, so for example, E double prime by E prime, okay, which is actually pretty much called as a tan delta. Okay, is tan delta, which measures how much viscosity is compared to its elasticity, tan delta. So you can understand in a single measurement, single data point. Again, you can do the measurement at an instant of time. Say, for example, time t equals to 1 second, say, for example. It can be, at a given temperature, variegated temperature, and frequency is inverse of time, so automatically. So you are getting again the physical properties, which is a dynamic property of the material from that. Okay. And then what I'm telling you, in same thing, if you realize from the angle of rheology, basically, this, what I told you, this viscosity measurements, or this the modulus, I'll call it the viscosity here. Once you measure it, it's another perspective of it in the terminal region. Okay, and there you measure, you get some eta prime and eta double prime. Then eta prime signifies the viscous flow, eta double prime signifies the modulus of it. So again, to look at two terminologies, don't get lost between two terminologies, modulus and viscosity. Those are all the way same. One represents more of a solidus character. When solid dominates, that will see it from the modulus point of view. When the liquidus state dominates, that will see it from the viscosity point of view. Okay, and this is about the dynamic conception. I mean, you can consider it as statically also. As I said, what is modulus? Modulus is shear stress by shear strain, and at the same time, if you look at viscosity, which is nothing but shear stress by shear rate. Okay, so it's your perspective how you look it upon. It's nothing alien. Okay, it's again I would say it's related to the physical properties of the material only. Okay, modulus again depends on so many things. Modulus depends on viscosity, depends on density also. Okay, so that way it's a physical property of the material. Another question, what Mr. Rakesh Upadhyay wrote to me in my email. Again, I mean, you please try to put it in a forum question. Okay, I'll not entertain much into my email. Okay, And also, I have with my two TAs, Ms. Ramya and Piyush. Okay, please try to. I think so. You get the connects from directly from there, the module. Okay, please try to write to them. I'll definitely adjust to this. Okay. One of the questions, Rakesh, I must thank you for that. It was again a mistake again. See, in one of the questions, question 6, I suppose, in one of the weeks, a Brookfield is commented, how does the selection of spindle size affect the measurement of the viscosity? Okay, so its answer is B is correct. Okay, Ramya, is it so? The larger spindles are used for higher viscosity. Okay, so that is the right answer. Is it the correct one? So the wrong answer was given. I will take care of that right to NPTEL so that in these particular things, the marks can be well taken care of. The right answer is B again. Thank you for that. But I must say, no, your clarification on that question number 7, the complex viscosity as a function of frequency measures, you have answered, the answers can be anything. But actually, really, what I taught you from that point of view, the answer of molecular weight distribution is more correct. Okay, please refer to that. And Rakesh, thank you once again for thanking me. But it's again, it's not in the outset of the NPTEL courses. That is my professional part is another part. Okay. So now let's try to quickly brief you about the upcoming classes. See, week 5, which will be emphasizing on importance of polymer compound. Okay. See, polymer, when I say rubber, compounding is very relevant terms. Okay. Without a bunch of additives, adding them in a judicious manner, okay, you don't get a useful rubber material basically, because rubber lacks in many aspects, although it has 3 important attributes. One is a elasticity, another is a hyperelasticity, another is a thermoelasticity. Okay? So these are the unique properties. Later 2 is very unique in rubber. Okay? But rubber as such has a very weak structure. It has a double bond somewhere for cross-linkability, ease of rotation of the bonds, as I told you. But at the same time, if you keep it in environment, it's susceptible to degradation by oxygen and ozone. Its strength is not sufficiently high enough, so you have to reinforce it, and so on and so forth. So compounding really plays very utmost important role there. So once you add several additives, those basic parameters like the shear viscosity, dye swell as a function of shear rate, okay, which is essentially related to normal force difference as a function of shear rate, okay, and the constitutive equation altogether changes, okay, and that changes you have to take care. In plastic in general or fiber in general, okay, your compounding complexity is far less, but still then in a plastic, usable plastic, you may have a pigments, you may have several other additives, okay, like fastener and whatnot, okay. So that can actually effectively influences those properties, those constitutive equations that I talked about. So that particular part is basically and physically highlighted. Okay. So then I talked about the mixing. So this heterogeneity is very meaning a lot for this sort of a material, say rubber and plastics. Okay. You have to any point of time reduce the heterogeneity while mixing different ingredients which are apparently at different physical states. Some is liquid, some is solid, and so on and so forth. Okay. So what are the problems associated with them while mixing, and how to have a very uniform and well dispersed particulate mixed into a polymer matrix? Okay. And what are the problems associated in the industrial scale and their remedies? Although it's not exactly the rheology that we are talking about, but ultimately associated with the processing of it. So we have coined it very judiciously in week 6. Okay. Week 7 is all about the hardcore industrial processes, practices, techniques. So, for example, you want to make a continuous state of material, go for calendering. Whether you make it a solid material or you have a textile or a reinforcement element there, you talk about the molding, all these 3 types of molding, at least for rubbers, compression, transfer, injection, blow molding also, I suppose. So I try to touch upon. So extrusion, injection, vulcanization, and here also we have taken you through some of the classes on numerical problem solving. So unless you do it, the latest stage of it, that means week 8, which is applied rheology, more of a computational technique. Okay, how you solve a flow in a computational technique? How do you design a die of a to make a particular shape? Okay, minimizing those dies well, making it to more perfected one. Okay, so although another thing also is quite relevant, which I could not touch it upon in another platform, in another place I'll touch upon, is the mold design. The die design part is taken care, is based upon one of my students, work here, PhD work. So briefly, how you can do your own die design. Okay, die design, again taking the help of rheology, solving constitutive equation by a computational technique. I specifically, showed you a fluid mechanical technique where we used the finite element techniques on top of fluid flow, basically, to design a perfected die. Only remember here, I consider only the, we consider the die zone of it. That means die land to die, then it's coming out, that part only. We remember, if we happen to do it for a whole range of barrel of the extruder, starting from the fluid to the end, it would have been a more rheologically complex system. It needs more supercomputing or other sort of facilities here. But only the basic things I took you to where it leads, why you take that courses ultimately. Also, it's up to you to take it forward and learn it more. So hope this quick elaboration has helped you having the grasp of the subject and create or boost some interest on the upcoming lecture. Please stay tuned. My advice will be go by each lecture of week 5, 6, and 7, and 8. Okay? Then only you will have a grasp of it. No matter how much marks you take it, but if you cannot apply that particular things you are learning from this particular course, it's not and void, I would say. Okay, so it's more important, like, you have a good grasp on the subject, so that at given any point of time, remove your slides, remove your books, you should be basically fundamentally able to tell how a machine design, a process equipment design can be possible. If my material is this, material is this, forget about that. It's a natural rubber, forget about that. It's a polyethylene, forget about that. You just try to, as an engineer, you must know what is the constitutive equation that particular polymer obeys at a given temperature and frequency or CR rate, and then try to put it in that constitutive equation into the apply several boundary conditions during the flow and try to have a solution of it. Okay, by numerical technique, which is a computational, obviously these days. Okay, so that's how your lookout should be. Your lookout should not be what I added up. Okay, but your lookout should be, okay, if I'm supposed to add this filler, this much of filler, pH or filler in a polymer, how the rheological constitutive equation changes like. So once you have that grasp, and then solving technique, how to have a solution. See, your end question that your manager will ask, that your owner will be asked, your employer will be asked, I don't know what you are talking about, what constitutive equation you are talking about. Give me the numbers. Give me what is going to be the dice per percent. Give me the number. If it is so, if this is equipment is such that this is the operational condition, what is going to be the surface roughness of the material? My customer demands this should be the maximum surface roughness we can tolerate. So within that limit, give me a solution of that for a given particular thing that you should be able to do. And that is the essence of the applied processing, basically applied geology, basically. So this is where you'll be will take you through ultimately. Okay. Again, I am very indebted to my TS, particularly Ramya and Piyush, who has helped me. Again, I beg your apology that while doing it timely basis, 1 or 2 questions, maybe you don't get it up to satisfaction. Had it been a full-length examination here, I really have evaluated you, giving you some really problems, and that you have to solve it, rather than just hitting numerical choices and answers. Okay. So that's what my sort of a philosophy is. Okay. So please stay tuned. Hope you have gained something. I'm going to gain some more. I promise you. Okay. So Ramya, please quickly check if there is any forum question. Online question or live questions there. If not, pretty much covered. If you have something, I'll give you 1 or 2 minutes, please. you just put your questions in the message box, and we'll try to share you back. Otherwise, we'll try to close our live session of today, the first live session of the renowned course on rheology today over here. Okay. So anything, should we stop it now? We are not getting any questions so far. Can you please stop the live session now for the day? Hello? Mr. Suman. Mr. Suman, we are pretty much done. Are you there? Am I audible?